In section 5.2, we're going to talk about a new kind of function. We're going to talk about exponential functions. Exponential functions are not lines. In the solve it area, I want you to write this down. Y equals 3 times 2 to the x power. That is an example of an exponential function. Now ignore the 3 for now. I want you to look at the 2 to the x. If you notice what happens here, I'm just going to plug in values of x. I'm going to pick random numbers. If you take 2 to the 0 power, that's 1. 1 times 3, that's going to give us 3. If you plug in 1, 2 to the first power is 2. 2 times 3 is 6. 2 to the second power is 4. 4 times 3 is 12. 2 to the third power is 8. 8 times 3 is 24. You will notice that every time you have another power, you're multiplying by another 2. And that's what we mean by growing exponentially. This problem is going to start gradually and then very quickly get bigger and bigger. So if you look at in the middle of the page, in the gray region, this says essential understanding. Some functions model an initial amount that is repeatedly multiplied by the same positive number. In the rules for these functions, the independent variable is an exponent. That's your letter. Your variable now becomes the exponent. Keep in mind that this is when you have an exponential function. You need to look for this. That. If you have a variable as an exponent, you will have an exponential function. I want you now to look at page 291 at the bottom of the page. The definition of an exponential function is that it is a function of the form y equals a, that's your coefficient, times the base, which is b, taken to the x power. Some things you need to know though. A cannot be 0. If a was 0, 0 times anything is 0, you would not have a function. B has to be bigger than 0. B has to be bigger than 0. That's important to note. B has to be bigger than 0. B cannot equal 1. And the reason why B cannot be 1 is because think about what's going to happen if you take 1 to any power. 1 to the 5th power is just 1. 1 to the 8th power is 1. No matter what you get, it's going to be the exact same number. So it's not going to be an exponential function. And then the other thing you need to know is the power. The x must be a real number. Now we really haven't talked about imaginary numbers yet, but you probably need to know, or you need to know, that x is also a real number. So we have 4 separate things that you just need to know based on just looking at this. A cannot be 0, B cannot be 1, but it also must be bigger than 0, and x has to be a real number. So x can be any number you want, as long as it's a real number. So look at the 2 examples at the bottom. In the first box, the red line, the curve, the red line, notice how it starts off really, really close to the x-axis, and then it grows really fast. That's if you have 2 to the x power. But now you have negative 2 to the x power, and now your graph reverses. It now goes down. And then the next graph is 1/2. 1/2 to the power, and then negative 1/2 to the power. Now, this is going to be kind of I'm hoping you understand this. Think of it this way. If this number, and I'm going to look back at on my page here. Look at B. If B is bigger than 0, bigger than 1. If it's 1, nothing changes. If B is bigger than 1, what's going to happen when you keep multiplying that number by itself over and over again? For example, 3, or 1.2, or 9. it's going to keep growing. Your number, as you multiply it by itself, is going to keep growing. But if this number is less than 1, like in the second graph on page 291, if you take 1/2 times 1/2, it becomes 1/4. If we multiply it again by 1/2, that becomes 1/8, 1/16. It actually keeps getting smaller. This number keeps getting smaller. So if b is bigger than 1, the number is going to grow. If this number here is less than 1, the number is going to decrease. In the first part of your homework, you're going to be asked to evaluate an exponential function. The Got It problem at the top of page 292 says, an initial population of 20 rabbits triples every half year. The function f of x equals 20 times 3 to the x gives the population after x half year periods. How many rabbits will there be after 3 years? So this is a little tricky in the sense that x represents a half year. So x is a half year. I want to know, after 3 years, how many rabbits there'd be. So 3, you're not going to plug in 3 years because x doesn't represent years. X represents half a year. So what would you plug in for x? You plug in 6 because there are 6 half years within 3 years. So 20 times 3 to the 6th power. Please make sure you follow order of operations. So we plugged in f of 6. That's going to give us 20 times 3 to the 6th power. 3 to the 6th power is 729. And 729 times 20 gives us 14,580 rabbits. So, after 3 years, we would have over 14,500, or we would have 14,580 rabbits. Example number 1. An investment of $5,000 doubles in value every decade. The function f of x equals 5,000 times 2 to the x power, where x represents the number of decades, models the growth of the value of the investment. How much is the investment worth after 30 years? X is the number of decades. A decade is 10 years. So how many 10 years are in 30 years? It'd be 3. So we're going to plug in 3 for x. So that means we're going to find the evaluation of f of 3. 5,000 times 2 to the 3rd power. That would be 5,000 times 8. And 5,000 times 8 is going to be $40,000. All right, our Got It problem on problem 2 is going to be graphing an exponential function. So now you're going to graph. Y equals half, or 0.5, times 3 to the x power. Now, knowing this number here is bigger than 1. Therefore, your graph is going to be going uphill. Because this is positive, your graph is going to go uphill. If you look at b, b is y equals negative 0.5 times 3 to the x power. This means that it's still going to go up, but this negative here, when we times it, is going to make it go down. So you should have a kind of understanding how to graph this. Now you have 2 options to graph. You can't use slope, you can't use intercepts. You got to either use a t-table or use your graphing calculator and just use the table function. If you go to the table function, it gives you all your table values. But what I would do is I would make a t-table, and I would pick, if you're doing problems like these, like 5 values. So I would pick, I would say 4 or 5, that's fine. So if you plug in 0, this should be fairly easy. 3 to the 0 power is 1, 1 times 0.5 is just 0.5. Plug in 1, that would be 3 to the first power, which is 3. 3 times 0.5 is 1.5. 3 to the second power is 9. 9 times a half is 4.5. And 3 to the third power is 27. 27 times 0.5 is 13.5. So if you graph this, I'm actually going to use graph paper. That's a better option here. So let me erase that. All right. When we graph this, 0.5 is going to be here. 1 and 1.5. 2, 4.5. And then 3 is off the chart. It's going to be way up here. So you'll notice that this is starting to increase quite rapidly. Now, one piece of advice I want to tell you. On this side of the graph, it is going to be getting closer and closer to the x-axis, but it will never cross it. This will never cross the x-axis, ever, because this value is never going to be 0. It'll get closer and closer to 0, but don't ever cross this near the x-axis. Now, later on, we're going to learn what an asymptote is. An asymptote is the line that it approaches here. So we'll talk about that later, but notice that this was never going to cross the x-axis. So let's now do B. In B, and once again, you can count by however many you want as well. So you could count your graph by 2s or 4s or 5s. Here I'm going to start with just, let's do -1. 0, 1, and 2. If I plug in -1, 3 to the -1 power is going to be 0.3 repeating, or 1/3. Now once again, you can use your calculator for that. You can take 3 to the -1 power, and that's 1/3. And then if you take -0.5 times 1/3, you're going to get -0.17, and I rounded it. It's going to be -1.6 repeating. Plug in 0. 3 to the 0 power is 1. 1 times -0.5 is -0.5. Plug in 1. 3 to the first power is 3. 3 times -0.5 is -1.5. 3 to the second power is 9. 9 times -0.5 is -4.5. You'll notice it's the same numbers, except now they're negative. So we graph the first one, -1 and -1, -0.17. 0, -0.5. 1, -1.5. And 2, -4 5/10. You'll notice that this graph starts going downhill really fast. Now, it's never going to actually, whoops, that's really bad. It's never actually going to go straight down, but it'll actually get steeper and steeper as it goes down. And up here, it gets closer and closer to the x-axis, but it'll never cross. And so that's your graph. All right, in this example, y equals -1/3 to the x power. Notice that this 1/3, if we keep multiplying it by itself, the number is actually going to get smaller and smaller. So this graph is going to look the opposite. Since it's negative, we're going to start at the bottom. It's actually going to go up, and then it'll actually get smaller and smaller, or closer to 0 as it goes to the right. It's the complete opposite of what the last two graphs look like. So I'm going to make a t-table. So let's just plug in 0, 1, 2, and 3. Okay, we plug in 0. 1/3 to the 0 power is just 1. This negative is here, so we're going to get -1. Now if we plug in 1, 1/3 to the 1 power is just 1/3. 1/3 times negative is -1/3. Now we're going to plug in 2. 1/3 to the second power is 1/9, so this is going to become -1/9. Then we times it by a third again. It's going to become -1/27. So when we graph this, 0, -1, 1 negative a third, 3 negative a ninth. You'll notice that this, oh, I'm sorry, 2 negative a ninth. Negative 1/27th. You'll notice it'll keep getting closer and closer to the x-axis, but it will never cross. So your graph would look something like this. And that's how you draw it. For example 3, for problem 3, you're going to be graphing an exponential model. These are all real-life problems. For example, exponential functions deal with problems such as someone gets the flu. They pass it on to 3 people. Each of those people pass it on to 3 people. How long does it take until someone spreads? Talks about population. In example A, in the Got It, it says this. You can also zoom out to view a larger area on the map in problem 3. Now we're not doing that one, but basically, when you look at a map, you can zoom in or you can zoom out. So in this problem, we're talking about the function f of x equals 100 times 4 to the x power. This models the percent of the original area of the map shows after zooming out x times. So x is the number of times we zoom out. Once again, what I would suggest you do is just punch into your graphing calculator, use the second table function, and you can just get your t-table right from there. But if you do this, negative 1, 0, 1, 2. If you plug in negative 1, now this is all basic math. I'm hoping you can do a lot of this in your head. 4 to the negative 1 power is basically 1/4. So if you take 1/4 divided by 100 divided by 4, or 1/4 of 100, you're going to get 25. 100 times 4 to the 0 power is going to give you 100. 100 times 4 to the first power is going to give you 400. That's 100 times 4. 100 times 4 squared, that's going to give you 100 times 16, which is 1600. You will notice that it increases rapidly. Now, when you graph this, notice I'm labeling this f of x since we're not talking about y here. I'm going to label my x, which is the number of times you zoom out, by 1s. And I'm going to count by 200. 2, 4, 6, 8, 10, 2, 4, 6. So 200. So this down here represents number of zoom out, number of times you zoom out. And f of x is the percent of the original area. So if you graph this, negative 125, 0, 100, 1, 400, 2, 1600. You'll notice it goes up really fast. Now in this problem, notice that I use the negative 1. I only used it to kind of help me my curve of my arch. Notice I didn't connect it though, because this is the number of times you zoom out. You can't zoom out negative 1 time. So I started here at 0 and went that way. I just use that as a guide. So it's completely up to you what you want to do. But that's how you graph it. B, what is the percent change in area each time you zoom out in part 1? Or in part A? So what is the percent change in each time you zoom out? So, part B. So if you go from 25 to 100, so we're looking at the first number to the next, percent of change would be, what is the percent when you increase? Now in this one, what are you increasing by from 25 to 100? 75 over the original amount. Now you really, honestly, you don't even need that. Just take 75 divided by 25. It's 3. If you times it by 100, it's 300%. If you went on to the next one, 100 to 400. To find the percent of increase, you have to subtract the two amounts. So it increased by 300 divided by the original amount of 100. 300 divided by 100 is 3. You have to times that by 100 since we're doing percent. Remember, 3 is just a decimal. You have to change it to a percent, so it's going to be 300%. If you keep going, it's going to be the same thing. So part B is 300%. In problem 4, this is the last thing we're going to do. This is on problem page 295. We're going to be graphing an exponential model with a vertical shift. That's when your equation, when it would say like plus 5 at the end, we'd shift it up 5 spaces. Or minus 2, we'd drop it down 2 spaces. We're going to skip the got it and go right to practice number 7. So number 7. Tracy's normal resting heart rate is about 75 beats per minute. During a strenuous workout, her heart rate increases 65 beats per minute, up to 140 beats per minute. When she begins her cool down, her elevated heart rate decreases by about 40% each minute. So Tracy's heart rate in beats per minute after X minutes of cooling down is given by... So now you have two options. You can just use your t-table or use your graph on your graphing calculator. I apologize, my phone just went off. Alright, so in this problem, a lot of you look at this and go, oh my gosh, there's so much to this problem. But all you have to do is graph this equation. So you pick anything you want, plug it in, times it by 65, and then add 75. You could just do this. And then your entire graph just moves up 75. All you have to do is add 75 to everything. So let's make a t-table. If we plug in 0, 0.6 to the 0 power is just 1. 1 plus 65 is just 65. And then it shifted up 75. So 65 plus 75 is 140. 1. So 1 is 0.6 to the first power, which is 0.6, times 65, which is 39, plus 75, which is 114. Notice that this is going down. Why is this going down? Because your base is 0.6. And every time you multiply 0.6 by itself, it gets smaller. Plug in 2. 0.6 times 0.6, that's to the second power, times 65 plus 75, that gives me 98 and 4/10. Let's do one more. 3. 0.6 times 0.6 times 0.6 times 65 plus 75 gives me 89.04. So if you graph this, one, 2, 3, and I'm just gonna go by 20s. 20, 40, 60, 80, 100, 120, 140. So 0, 140, 1, 114, 2, 98.4, and 3 is 89. This graph is going to be doing that. Everything has been shifted up. Your normal graph would actually look something like this. Your normal graph would look something like that. And then everything gets bumped up 75. You don't need to graph this. I mean, this part you don't need that red line, you don't need to graph. But that would be your answer. And as I was graphing this, I noticed I made a mistake, and this is a perfect example of of how easy it is to make a mistake. 0 represents what? I mean, what does X represent? X represents the number of minutes of cooling down. Number of minutes can't be negative. So this part of the graph right here, with the arrow on the left side, I should not have drawn. You should start here at the 0, and then it goes down from there.